I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for the students, and just ask you to just bless our work today, Lord. In your name I pray. Amen. So, we are now to chapter 10, believe it or not. I somehow got 2 days ahead. I guess it has something to do with me making a video. But I thought I was behind, so I'm very confused by this, but now I'm very much ahead. And so I'm going to take some time to actually read a few quotes in here, because I think they're interesting. So first of all, the story of power series and how we come to a technical understanding of power series is a story which arches over several hundred years, really. A lot of the major events in this story probably happened, for the most part, in the 19th century, all right? So the 19th century, the start of the 19th century, we saw Fourier, for example, doing this madcap stuff with solving partial differential equations by saying you could take infinite sums of sines and cosines to solve partial differential equations, right? Which is just like, what? But it worked. I mean, found solutions, right? But on the other hand, inattention to details of convergence and divergence for series, trigonometric series, will get you into trouble, all right? Like, if you just go and you can like differentiate something convergent and make it divergent, like weird stuff happens for trigonometric series. And so people started to be aware that, you know, we need to be more careful about analysis. And in the process of, you know, studying different questions over the 19th century, we became aware of different concepts which could be used to clarify both the questions and the solutions to the problems. So that's a lot of what chapter 10 is about. It's about bringing us to the point of understanding how complex power series can be discussed carefully, and also just what theoretical tools are developed and useful for studying them, all right? So start with a quote. This is what Abel had to say, like, you know, abelian groups, that Abel. He said, if one examines more closely the reasoning which is usually employed in the treatment of infinite series, he will find that by and large it is unsatisfactory, and that the number of propositions about infinite series which can be regarded as rigorously confirmed is small indeed. This is pretty withering criticism from a mathematician in public discourse, right? I mean, that's pretty something. Guterman in 1838 said it's a fact worth noting that the series just found have all the same convergence rate. Now, this is a new idea. This is one of the things we're going to talk about today. This same convergent rate is the notion of uniform convergence. Weierstrass is credited with this idea of uniform convergence, which I'll explain today. And so Weierstrass was, you know, he had a lot of influence in the mid-19th century. And then, of course, Koshi plays a large role in this story as well. But, all right, I'm going to push along here. So that's what's on the final. But let's see here. Anyway. Obligatory, yeah. But, okay, so point number one, let us discuss sequences. What are complex sequences? A sequence of complex numbers is if you could take it to be a list of complex numbers, right? It's a function from the natural numbers to the complex numbers. That's a sequence, a complex sequence, right? And we can define the limit of a sequence in the usual way. We say a sub n goes to a if for each epsilon greater than 0, there exists some n in the natural numbers such that the difference between a sub n and the limit is less than epsilon whenever n is beyond big N. This is the same definition that we gave in Calculus 1 or 2 somewhere, except, of course, absolute value is now replaced with, well, complex absolute value or modulus, if you like. All right? We can talk about bounded sequences. If you've got if you've got a complex sequence and the modulus is less than r for all n, then it's said to be a bounded complex sequence. All right? Convergent sequences have really nice properties, like the sum of sequences limits to the sum of the limits, right? And the product theorem, if Sn and Tn both converge, they converge to the product of their limits. We have a quotient theorem, provided that the limit of the denominator terms are limiting to non-zero. You have a in-between theorem. Now this one is only for what? Is this for complex sequences? No, I mean, if you read on, this is only for real sequences, right? If I gave you 1 plus I and 1 minus I, which one's less than the other? 1 plus I or 1 minus I, which one's smaller? Right, you shouldn't answer this question. It's not a reasonable question. Unless, of course, you decide to give the complex numbers the lexicographic ordering, where you take like words in an alphabet and take the reals to be the first letter and the imaginary part to be the second letter, and then you could use this lexicographic ordering to order the complex numbers like that. But if you did that, it has zero to do with the algebraic structure of the complex numbers. So it's an ordering, but it's not an ordering which is in any way sympathetic to the algebraic structure of the complex numbers. Anyway, of course, this is for real sequences. Here's our favorite theorem from Calculus 2 we don't understand. A bounded monotonic sequence of real numbers converges. We can also talk about subsequences. What's a subsequence of a sequence? Just what it sounds like, right? You take some subset, some sequence that's taken from just taking parts of a sequence, but maybe not all of it, right? A subsequence, maybe just the even terms or just the odd terms, right? You can then define the so-called lim sup and the lim inf. The limit supremum is the upper bound of all possible subsequential limits. The lim if is the lower bound of all possible subsequential limits of a sub n. So a nice example, if you look at the example that's minus 1 to the n, so it's going 1, minus 1, 1, minus 1, 1, minus 1, right? If you look at the lim sup of that, it's 1, because you can take the subsequence, which is just 1, 1, 1, 1, 1. If you look at the lim inf, you get minus 1, because you can take the subsequence minus 1, minus 1, minus 1, minus 1. If you had a sequence which was based on like tangent, like you say took tangent of n, the lim sup and the lim inf would both be infinity and minus infinity respective. Because if you look at tangent of a natural number, if you go on out, you never hit infinity, right? Because tangent of pi over 2 or minus pi over 2 is infinity minus infinity respectively, right? But you'll never actually hit that infinite thing, but you'll get infinitely close to it as you cycle through integers going out to infinity, right? So if you think about tangent of n, that would have a lim sup and a lim inf, both of which are infinite. So that's typically allowed when we discuss lim sup and lim inf. Anyway, I don't do too much with that in here. Sorry about that. Stop that. Shush. Oh. Hey, it was about math. My brother's very excited about some particular question on the Stack Exchange right now that's, anyway, not important. This discussion is continued in real analysis. I will not continue it here. We need the concept of lim sup and lim inf on rare occasions in here, so I just throw it out there. There is a place where it comes up. Next, theorem 10.10. If we have a complex sequence, right, then this sequence converges if and only if the real and imaginary subsequence component sequences converge, right? This is a specific example of what I call the vector limit theorem in calculus, in advanced calculus. I think I've talked about this actually before, but not for sequences, for functions, right? We also had an epsilon delta definition for the limit as x goes to a or h goes to 0. That's a related but different idea, yeah? So, but the proofs are very much the same for the sequential. Oh, no, don't do that. I was trying to turn up the brightness on my screen, and I failed. But the proof is maybe worth looking at here for a minute. Suppose we have x sub n goes to x and y sub n goes to y. Then it's an immediate consequence of the vector limit theorem that, well, this is actually not even the vector limit. This is just the sum of this sequence plus that sequence goes to the, this is the sum of the limits is the limit of the sum theorem, and also that you can pull a constant out. So that's just that. Since this and that separately converge, it converges to that. Conversely, if you suppose that Zn converges to Z, right, we'd like to prove that Xn goes to X and Yn goes to Y, all right? And so the crucial inequalities here are that the difference between Xn and X is smaller than that, right? So what this is saying is that the real component of a complex number has a magnitude which is smaller than the length of the complex number. And this is the imaginary component of that complex number is smaller than or equal to the complex number, right? Those inequalities are, I think, clear. And if you have epsilon greater than 0, since as Zn goes to Z, that means we can pick n, big enough such that for n, little n beyond the big N, we have that the difference of Zn and Z is less than epsilon, right? So that means that this is less than epsilon, right? And that is less than epsilon. So that implies that xn goes to x and yn goes to y, just like we like. So it's an important theorem, right? Because sometimes when you're looking at a complex sequence, it's convenient to look at the real and imaginary part of the sequence and to study those separately. But not always. Right? You've seen this over and over in this course, right? When you deal with a problem, should you break it up into real and imaginary parts, or should you study it as a complex problem? But this is a decision we make in every problem we work in here, right? And sometimes choosing the path that's the wrong path comes with a heavy price, doesn't it? I mean, I've experienced this. What's a Koshi sequence? A Koshi sequence means that if you go far enough out in the sequence, you can make the difference between terms as small as you like. So it's essentially a sequence which the tail kind of pinches to nothing. So for each epsilon greater than 0, we can find an n such that for m and n beyond that, and we just, without loss of generality, suppose m is less than n, that implies that the difference of am and an is less than epsilon. This is a Koshi sequence. Now, definition, a space is said to be complete if every Koshi sequence converges, right? The quintessential example of a space which is not complete would be the rational numbers, right? Because we can take a rational sequence, which is Koshi, and yet does not converge to a rational number. Can you think of a rational sequence like that without looking at what I say here? Yeah? Oh, you look. All right, I'm not looking. I don't know if this is what I have here or not, but I often think about pi, right? If you just think about the real number pi, if you take any finite decimal expansion of that, right, that's a rational number. And so you could let your sequence be the first n digits of pi. So like n equals 1 is, I guess, 3. What's the first digit of pi? It's 3, right? No? Is it 3.1? 6? Okay, 3. Okay, don't do that to me. Anyway, so n equals 2, 3.1, n equals 3, 3.14, 3.141, 3.1415, 3.14156, 3.145. Okay, I'm just making it up now. But I stumbled there, and you stopped believing me. You have to, when you make up digits to pi, you have to state it with more authority if you want your audience to believe you. There's not, yeah, especially the first one. Good point. Usually, in a given audience of math students, you won't have somebody there who knows more than the first 5 digits of pi. If you've got the first 5 digits down, you can make them up after that. Just be sure to be kind of random. All right? Just saying. It's a teaching trick for you. Anyway, my point is that, and this is borrowing a deeper fact which I have not proved, but in fact, the limit as n goes to infinity, of course, gives you what? Pi, right? Is pi a rational number? Well, you can prove that it's not. So there you go. That's a rational sequence which converges to an irrational number, which goes to show you, and yet, if you take the difference between two of these really far out, they can be shown to be as small as you like, right? I mean, you can, however small you want to make it, you can just go far enough out in the decimal expansions, because decimal expansions get smaller and smaller and smaller. So you can easily see that that's a Koshi sequence, and yet it does not converge to a rational number. It converges to pi. So rational numbers are not complete. But complex numbers are complete, and so are the algebras that we studied earlier. All right. In fact, this is really not an algebra thing. It's just I suppose a set theoretic thing. If you have Rn is complete. Matrices with real components are complete, given the right notion of what distance is. So most things we study that have real entries are complete. That's very nice because it's often easier to prove a sequence is Koshi than it is to prove directly that it converges. Checking the Koshi condition in a complete space is often easier than checking direct convergence. So infinite series is our next section. And so I'm sorry this is a little bit boring in the sense that my definitions are really just the same ones that you saw in Calculus 2. All right? I mean, this is the Calculus 2 definition of a series. A series is an infinite sum, and we understand that sum to converge if the limit of the sequence of partial sums converges. Right? This is an old story. But now the contestants in the story are now complex numbers. But otherwise, the song remains the same, right? I mean, this is a series with term a sub j, and we say it converges if and only if the sequence of partial sums converges to S. S is the sum of the series if it exists. Yeah. And we have theorems for series, right? If we have two convergent series, the series of the sum is the sum of the series, and you can pull a constant out like that, right? And the proof of these really just relies on the corresponding properties for limits of sequences, because remember, a series is defined to be the limit of sequence of partial sums. So because the finite sum is additive and homogeneous, and because we have the corresponding theorem for limits of sequences, we get corresponding theorems for series. It's very straightforward. We can also look at a complex series as being decomposed into a real and imaginary part. If the real and imaginary part of a complex series separately converge, then the complex series converges, just like the corresponding theorem we had for sequences, all right? This one's a little bit more exciting. What's this say? Now, this is a sequence about what? Is this a complex theorem? What kind of theorem are we looking at here? Yeah, this theorem's keeping it real. That's right, it's for real. See, because I've got an inequality here, so it must be that we're talking about a real sequence, because we would not write an inequality for a complex sequence directly like that. And this is the comparison theorem, right? If we have a larger series converges, then the series summed from smaller terms must also converge, right? And that assumes what? That assumes that they're not negative. This is important, that 0 be below the a sub k, right? If you don't have the 0 here, it could be that your a sub k's are getting exceedingly large and negative, and you could still have a divergence in the other direction, yeah? Okay. Now, this is maybe something you haven't thought about as much, but I don't know if you've thought about this or not, but how do we actually define a finite sum? Like, what's the sum j equals 0 to an n of a sub j defined to be? You can define this recursively. So it would be a sub n plus the sum j equals 0 to n minus 1 of a sub j, right? And if n equals 0, we do what? Sum j equals 0 to 0 is defined to just be a sub 0. So that starts at, what's the sum j equals 0 to 1? It's a sub 0 plus a sub 1. We give a couple of those, set up the recursion, you've defined finite sums for arbitrary finite size. And then you can use that definition to prove careful things about the finite sum of a sum being the sum of the finite sums, and that you can pull constants out of finite sums, right? If I'm not beaten down and if I'm not too demoralized, I'll have linear algebra prove these things. Did I have you guys prove those things? Oh, this is a window into my mental health right there. So, yeah, I digress. Anyway, my larger point, though, is that you can solve the recursive definition for a sub n here. What do you get? A sub n is equal to the sum j equals 0 to n of a sub j minus the sum j equals 0 to n minus 1 of a sub j, right? And so what happens, if this is a convergent series, that means that the limit as n goes to infinity of this is s, and the limit as n goes to infinity of this, by a simple substitution, you can see that that should also be s, right? because if n is going to infinity, surely n minus 1 is also going to infinity. So look at it. This is going to s minus s, which is 0, which shows you that for a convergent series, you must have that a sub n is going to 0. This is a proof of that nth term test that we tried like mad to teach you in Calculus 2, right? Well, you guys made it here. You're the ones who understood it, right? Right? Okay. Sure? It's always I tell you, that test in Calc 2 is hard to grade, because it doesn't matter how long you talk about the nth term test and how many times you cover the harmonic series when you teach this material for yourself to try it. You will still have 80% of them use the nth term test to prove convergence. It makes your head want to explode. But anyway, nth term test. Oh, I'm sorry. What was I saying? J'th term test. Yes. Now, of course, this is not sufficient alone for convergence. This is a no-go theorem, right? If a sub j does not go to 0, then we get that it doesn't converge. That's its main use, all right? Proposition 10.2.6 is near and dear to my heart. This is the geometric series. We will be using this a lot. This one you need to understand carefully. So if we have, let's see here. I don't know why, there does not need to be a z sub j here. That's a typo. This is just supposed to, what on earth? I just don't even know what that is. Just delete this. That's just, no. No. Oh, you know what you know what, I know what it's supposed to say. I know how to make this make sense. Why is this sentence here? It's a very silly sentence. What I was trying to say was that z to the j is a complex number, right? For any j that's either 0 or a natural number. Provided what? What precondition do I need on z? It could be 0. 0 to the whatever is still. We're not going to talk about 0 to 0 right now. Yeah, you try to get me into that. I'm not going to do it. Nice try. Good try. I know what you're after. No, I really should say z is a complex number, because then we can talk about a complex number to a power, an integer power, right? What is 0 to the 0 power as we've defined it, though? Ball back in your court. X, so I think it's 1 then, yeah. 0 to 0 is 1 for us then, yeah. If we use the exponential definition you just mentioned. Okay, although, wait a minute. I think that the one case that definition is not defined for is 0. Yeah, I think if you look back at our definition of z to the c, it's for z not equal to 0. So that won't help us. I said I wasn't going to talk about this. I seem to be getting... Okay, so if the modulus of z is less than 1, then we can prove that the sum j equals 0 to z, infinity of z to the n is 1 over 1 minus z. And on the other hand, if it's greater than or equal to 1, then this geometric series diverges. Do you remember how we proved the geometric series? Well, if you've forgotten, good news. It's right here. This is the same proof I give in Calculus 2, but instead of having x, we now have z. Or sometimes I'll use an r, right? The pirate proof. Let's see here. So now, if the absolute value of z is greater than or equal to 1, then the nth term test shows the series diverges, right? Because z to the power j for modulus of z greater than 1 is pretty easy to see that that's going to go to infinity. Anyway, it certainly does not converge to 0. If the modulus of a complex number is larger than 1, and you raise that to a power, that makes the modulus get bigger and bigger, bigger and bigger and bigger, right? And the angle's doing all kinds of crazy stuff going round and round and round, but who cares about that? The point is that the modulus definitely doesn't go to 0. And one of the theorems I could have written is that for a complex sequence to go to 0, that's going to be, that implies what? The modulus goes to 0, right? If a sub n goes to 0, then the absolute value of a sub n must also go to 0. Here's a question. Is it both ways? If the modulus of a sub n goes to 0, does that imply that a sub n goes to 0? Yeah, I think it does. Yeah, from 332. That was so long ago for me, though. So yeah, we can trade. We can look at the modulus, the complex, the absolute value of a sequence to judge whether or not it's going to 0. That's often useful. Anyway, so if this, then we've got divergence. But what if we don't? What if the distance from z from the origin to z is less than 1? In other words, this says we're what? We're inside the unit disk, right? Modulus of z less than 1. Then we can look at the nth partial sum, like that. And then, okay, fine, technically that's actually the, oh no, it is the nth. I'll shut up. I always debate whether or not I've labeled S sub n so that it is actually the first n terms. But since we started j equals 0, that's actually the first n plus 1 terms, but my labeling is that it's S sub n. This is not interesting, I'll shut up. Okay, so S sub n is this. If I multiply by z, I get that, right? And then if you subtract one from the other, you get a lot of cancellation, right? You get the z cancels the z squared cancels z squared, all the way out to zn canceling zn. And you're just left with the bookend, so to speak, the 1 from that one, and the zn plus 1 from that one. So you get 1 minus z equals to that. Now, since we're assuming that the modulus of z is less than 1, that means z is not equal to 1. So I can divide by 1 minus z, right? And I get that. But then you can actually, and as I always impress on my Calculus 2 students, this is a special and wonderful thing. We can actually calculate the nth partial sum. That is so rare to be able to just straight do that. But we did it. There's the formula for the nth partial sum. It's that. Wow. And so as n goes to infinity, this goes to 0 because the modulus of z is less than 1. And it leaves you 1 over 1 minus z, which of course is the standard geometric series result, but now for complex numbers. So I said in some sense parts of this lecture are boring because it's not different, right? The proof is the same as it was in Calculus 2. It's just that the same proof works for complex numbers, which is kind of beautiful. You can talk about a complex series being absolutely convergent. That would mean that the series of the moduli converges. You can prove that absolute convergence implies convergence. Well, wait a minute. What did I say here? I said a little bit more than that. I said if this is absolutely convergent, then we've got convergence. Oh, and we have that the size of the sum of the series is less than or equal to the series of the sum of the absolute values of the series. Right? So this is a little comparison theorem. Here's the proof of that. It's just, I think it's just direct comparison, actually. Let's see here. Suppose that this converges, which would be absolute convergence, right? And let's let a sub k be x sub k plus iy sub k. Check this out. So then the modulus of a sub k is the square root of that squared plus that squared, right? Just definition of modulus. And then, hey, is this greater than or equal to that? What have I done to go from here to here? Does it make sense that this, I just did what? I dropped a possibly non-zero term, right? So this is clearly larger than or equal to that. But this is the absolute value of x sub k, right? And similarly, you can show that the absolute value of a sub k is greater than or equal to the absolute value of y sub k. So by the comparison test, x sub k is less than or equal to that, which means that we have that this is convergent. And likewise, we get that the absolute value of the y sub k is smaller than the... So a comparison test gives us the convergence of both x sub k and y sub k's absolute values series. So in other words, we have absolute convergence of this real series, and we have absolute convergence of that real series. And then I refer you to the theorem from Calculus 2, which said that absolute convergence of a real series implies convergence of a real series. And that proves that this converges because we showed that that and that separately converge. Consequently, the complex thing converges. And the estimate here, I think, is, how do you, this has got to be in here somewhere. That may be a gap in my current proof. I'm not sure if I've actually shown this inequality. Of course, the other giant gap is assuming the real theorem, right? Now, for those of you who have not seen the real theorem, I reproduce it in the next couple paragraphs. This is the proof of the real absolute convergence implies convergence theorem. So then, again, a calculus 2 result. So if we look back at the geometric series again, we can ask the question, is the geometric series absolutely convergent, right? We've seen that the geometric series is convergent for the open unit disk, right, for modulus of z less than 1. Now my question is it absolutely convergent? And so, in other words, is this series absolutely convergent? Well, this is less than or equal to that. Let's see here. How do I get that? Yeah, it's a triangle inequality, but right, I mean, that's it. I'd be happier if I was applying the triangle inequality to the sequence of partial sums, and then taking the limit of that or something, like to be more careful, but this is, I would say it's not wrong, it's just incomplete. I wonder if what's down here actually justifies that. Let me see. Following Gamelin, I have this minus that. Well, that's the whole thing minus that. So if you look at that, we're starting with first n terms and from 0 to infinity. So if you remove the first n terms, you just go n plus 1 to infinity. But then you can make a substitution. You can factor out z to the n plus 1 from this, and it leaves you that. But then this, again, by the geometric series result, is 1 over 1 minus z, which gives us this. So that's kind of a sneaky calculation. The difference of this and that is that. So that says that the norm of this minus that is equal to the norm of that, which is less than or equal to, see, I've replaced that with that. That makes the denominator smaller and hence the fraction larger. And let's see, this inequality above gives us a bound on the error for the nth partial sum of the geometric series. Okay, so there's two things going on in this example. The one is just exhibiting that this is, in fact, absolutely convergent, point number one. Point number two, here's an explicit estimate on how close, if you truncate the geometric series at n terms, this bounds the error in the truncation of the geometric series at n terms. So this is a pretty useful estimate. Like if you wanted to approximate your geometric series by just keeping the first 3 terms, this tells you how much you're off by, right? It's an error estimate. All right. So if you're interested in the history of absolute convergence, you might look at page 29 to 30 of Vermeer, where he briefly describes the influence of Koshi, Dirichlet, Riemann on the topic. All of my historical comments in here are from this book by Reinhold Vermeer, who was one of the great, did a lot of work in theory of several complex variables, things like that, like deeper complex analysis in the early 20th, well, maybe mid-20th century. And he has a really nice book, which is one of the ones that my notes are based on. You don't have to look at it, obviously. I'm just, if you ever get interested, you can look at that. Section 10.3. Now this, finally, we're to the part of the lecture which I would say is genuinely new for many of you. Have you ever thought about sequences of functions before? What is a sequence of functions? You could think of it as a list of functions, right? For each natural number, you give me a function, right? So like f1, f2, f3, f4, da-da-da, where f1, f2, f3, f4, these are all functions. And this is complex analysis, so we're interested mostly in functions on the complex numbers, right? And so the first notion of convergence is so-called pointwise convergence. If we have a sequence of functions, and we need the functions to have a common domain, all right? So suppose all the functions have domain E. It's said to pointwise converge to f if the limit as n goes to infinity of fn of z is equal to f of z. So this is the first and most sort of basic concept of convergence of a sequence of function is just pointwise convergence. Now, it turns out that that mode of convergence is not very good for theory. Because a lot of things that, so one of the things you'd like in your theory of, sequential limits of functions is you'd like things like, for example, if you had a sequence of continuous functions, right, and they're convergent. So you have a sequence of continuous functions that converges to a function. It seems like, in a good theory, perhaps the limit function should also be what? Continuous, right? Or maybe if you've got a sequence of differentiable functions, then the limit function, if it exists, it ought to also be differentiable. It turns out it's kind of a pain to get these things to be true. And that's what we're going to be investigating here for the next 10 minutes or so. So here's an example to show you the subtlety. If we took the sequence of functions just to be monomials, so like fn of x is x to the n, and I'm just going to focus on real examples because real examples show you all of the danger. And then the cool thing that's going to happen is when we study complex functions and complex sequences of holomorphic functions, all of the trouble of real analysis washes away and everything just works. Because Cauchy's integral formula says that integration and differentiation are strangely and inextricably linked for complex functions. Look at Cauchy's integral formula. It's a relation between a derivative and an integral of a complex function. They're like on the same playing field, yeah? All right, intuition aside, here's a real example that'll get you messed up. So limit as n goes to infinity of x to the n. What happens here? It's 0 if you're between 0 and 1. It's 1 if x is equal to 1. Can you see that? If you plug in 1, what do you got? Limit of 1 to the n. What's the limit of 1 to the n as n goes to infinity? It's 1, right? What's the limit of any number less than 1 to the n as n goes to infinity? 0. So the limit function here, right, is this weird function that's 0 all the way up to 1, then it jumps to 1. Is this continuous? It is very much not continuous. And yet, the sequence that it's being formed from, that it's the limit function of, x to the n, is x to the n a continuous function from 0 to 1? I mean, it's a line, right? It's a line, it's a parabola, it's a cubic, it's a quartic. And if you start graphing these, you can see what's happening, right? See what's happening? This is the first thing in the function, first thing in the sequence. Here's the graph of the second thing. Here's the graph of the third thing. Here's the graph of the fourth thing. Here's the graph of the fifth thing. You see what's happening. Eventually, as n goes to infinity, you got this problem in the sense that the limit function, the graph of the limit function is this. Right? That's f. So, pointwise convergence, this is a sequence which has pointwise convergence. That's not enough to maintain continuity of the limit function. Here's another one. You can look at the function that, so another way to, by the way, another way to capture what I just said is that the limit as x approaches 1 from the left and the limit as n goes to infinity, these limits cannot be interchanged. See, because if I calculate the limit as n goes to infinity first, I get this thing which is what? It's always 0 except for when it's 1 at the limit point 1. So this limit is working out to 0, because remember, the limit as x approaches 1 from the left does not actually get to 1. It approaches it, but it never gets there, and all of those are 0. On the flip side, that's just, we've known that that was 1 since about week 2 in Calc 1, right? And so this limits to 1, and of course 0 is not equal to 1 where we come from. So you cannot commute these limits. Pointwise convergence does not play nice with the commuting of limits. This sequence, another example, G sub n. So what this is it makes, the graph is something like a triangle, and then it's 0. So and the triangles get more and more smushed as n goes to infinity. So they get more and more spiky. And the interesting thing about this calculation is I integrate this, I think I integrate that. What do I get? I get a half for any n. So the triangle, the tent is so constructed so that it's always got an area of 1 under it, all right? And so what you can see here is that if we take the limit as n goes to infinity of the integral from 0 to 1 of gn of x, I just showed that that's equal to 1 by these calculations, so that's why there's a 1 here. But on the flip side, as you go to infinity, gn of x, what it looks like is just a spike. It's everywhere 0 except the spike. What's the area under the spike? Well, 0. So the integral is 0 for the limit function. So again, we can't pull this limit, you know. The integral of the limit is not the limit of the integral. Now, I thought it would be good to have an example that works. This one, if we have x to the n over n, and you calculate, you know, the limit as n goes to infinity, you get 0. All right, and you can also calculate the limit as x goes to a. And so, in other words, I can commute limits as x approaches a and x as n goes to infinity for this function. We can, but you know, great. So it seems that there's hope for limits of continuous functions to be continuous, right? But there must be some property that this sequence of functions in example 10.3.4 has, which the previous two didn't. Now, before I get to that property, I would point out that the previous example still fails us as we try to maintain the differentiability of the limit function. So if you look at this, you take the derivative of it, you get back to x to the n minus 1, and we know that that's our first example. And so we've got that the derivative is 0, and it's 1. So we've got a discontinuous derivative like this. So if we do the limits in this direction, we get 0. If we do the limits in the opposite direction, we get 1. We can't. In other words, the limit of the sequence of derivatives is not the derivative of the limit function. So even though it allowed us to maintain the continuity, we lost the differentiability. All right. That brings us to the definition which repairs these examples. All right. And the definition is this. If we have a sequence of functions f sub n on E, and if we have f as a function of E, we say the sequence of function converges uniformly to f if for each epsilon greater than 0, there exists an n and n such that n greater than n implies that the modulus of f sub n of x minus f of x is less than epsilon for all x in E. I can draw a picture of what this looks like for you guys. So if E is perhaps this, I'll make a real picture because I have a hard time graphing complex functions on the board, you know. And so maybe this is my function f, right? And so if I make epsilon, you know, make your epsilon band, whatever you want. Maybe it's like this. So here's an epsilon band, right? Then it's saying that, you know, maybe if we plot the sequence, plot the values of the sequence, right? Maybe, I don't know, maybe this is the graph of f1. Maybe this is the graph of f2. Right? And then maybe beyond, maybe 3 and beyond happens to fit in here, right? So, in this case, I could choose my n to be 3. If I have little n larger than or equal to 3, the values for the function fit within an epsilon band of my limit function f. This is uniform convergence. All right, uniform convergence. And what I will show you guys is that we did not have uniform convergence for example 1. In fact, when you look at the possibility of uniform convergence for example 1, you find out that no, it's not uniformly convergent. And when you look at example 2, you again don't get uniform convergence. All right. But when you look at the third example I did, actually does have the uniform convergence property. If we look at the x to the n over n, you can actually prove that that has uniform convergence. I'll talk more about how we actually do that next class. Okay, I just want to share with you the punchline before we get into the... It's going to take me 10 minutes to explain this uniform convergence calculation. It's a little bit fussy. But here's some of the theorems which are true. If we have a sequence of complex valued functions, and if each f sub j is continuous on E, and if it converges uniformly to f on E, then the limit function is continuous. So in other words, the uniformly convergent sequence of continuous functions is continuous. This is actually a theorem for real analysis as well. The proof which is given here equally well applies to what is known as a metric space. It is also true, 10.39, that we can pass the integral and limits, like the integral of the limit is the limit of the integrals for a uniformly convergent sequence of functions. That is also true for both complex functions and real functions for which an integral is defined. I can't talk about what real functions for an integral are defined, though, because, hey, we don't have measure theory in here, do we? But here's a proof using the ML theorem. I'll do these proofs next time, probably. And anyway, so let me just tell you where we're going. I need to spend probably another half hour just trying to communicate these ideas to you. At the end of it, we have a set of theorems which we can apply to what we're really interested in, which is power series. Power series of complex numbers, right? Because what is a power series? A power series is a sum of complex functions, right? 1, z, z squared, z cubed, z to the 4th, z to the 5th, right? These are monomials. So the kind of sequence we're summing is a complex sequence of functions. That's a complex power series is formed from summing a sequence of complex functions, and we're going to be able to argue that those are in fact nice functions that are in fact uniformly convergent, and so forth and so on, and we'll have a very nice theory of complex power series. And that's the technical bedrock on which we lay a lot of the rest of the course, right? Anyway, that's where we're going. So thanks, guys. Hopefully the hurricane won't cancel class Friday, right? Well, it hasn't been canceled yet, so we're probably fine, right? Yeah.